A lot of students think that the definition of continuity is a very complicated topic. Well, I'm going to show you the best way to do it that's easy to understand. What is going on, math fans? I am Mr. Barnes, and I make math videos. If this is your first time to the channel, if you're looking to get better at math, then the best way to do it is subscribe. And if this video helps you in just a teeny little bit, give a like, drop a comment, say hi. I got lots of fans out there, so if you want to communicate with anybody in my community, you're more than welcome to do that. All right, let's get into the screen. All right, so hopefully you can see my screen now, and if I'm any good at editing, hopefully that's the case. So in today's video, as I said in the intro there, we're going to tackle a topic that for whatever reason I find is traditionally a little bit sort of conceptually complicated for students. So it's called the definition of continuity. So continuity itself basically just tries to explain what is happening at a particular location on the graph. Whether it's continuous means that you can draw a line without a jump or anything missing, or if it's discontinuous, so there might be a little tiny hole in the graph, there might be a jump in the graph, maybe there's an asymptote in the graph. So all these topics hopefully are somewhat familiar to you, and lucky I know a guy with a YouTube channel. If you need a couple videos that might sort of catch you up on these topics, I will drop them in the description, or maybe there'll be like a little thingy-majiggy that comes up along the way there. But yeah, so continuity is sort of, it goes hand in hand with a graphical concept. So in calculus, we have this definition of continuity that basically it's a test to see if a particular part of a function is continuous without having to do a graph. So that's obviously very useful because every time we get a function, we don't want to graph it to see what's going on. So a function is continuous at a particular point. So x equals a. So a is just like a number, 1, 2, 3, 4, 1.5, whatever it might be. If you sub the number into the function and you get back an answer, so it must exist. If you take the limit at that particular point and the limit exists, and I'm going to put in bracket because most often these are going to be piecewise functions, and that's what I want to talk about, is that one-sided limits must be the same. And then, of course, you got this last one, which says that 1 must equal 2. So the point that we found in 1 must be the same as the limit we found in 2 in order for it to be continuous. So let's put this into action. Let's do an example, and let's see where this takes us. All right, so we got a function here, and you can see it consists of 3 pieces: less than 1, equal to 1, and greater than 1. And we're asked to determine if it's continuous at x equals 1, and if not, determine if it's removable or not removable. So we'll see what happens first, and then we'll talk about that. So we'll do the definition, and this is how I start all these questions. I start with literally writing down number 1. And so the first part is, does f of 1, so a in this case is our 1, does f of 1 exist? So we literally have to find it. So we go to our piecewise function, and we're looking to where we have x equals 1. So this is x equals 1 right here, and we check to see if there was a value here, like a variable, we'd have to sub the 1 in, but it just gives us back that when x is equal to 1, our function is 2 always. So that's the first point. So f of 1 equals 2, therefore that exists. So we're good, okay? So whenever you break the discontinuity, a lot of times you can stop, because if you know what's happening, then you can stop and explain, or in this case, we've got to keep going. So the next step is we have to figure out the limit. So this is where a lot of times in these piecewise functions, everything goes wrong. So we'll go ahead now and we'll check this guy, and this is the left-hand side. And the reason why it's the left-hand side is because it's less than 1. And this is the right-hand side, and the reason why it's the right-hand side is because it's greater than 1. Literally, on the number line, 1 is here, This is the less than 1, that's the left side. This is greater than 1, that's the right side. So that's why we say left-hand side, right-hand side, because it's literally on the number line, that's what it'd be. So let's start with the limit. So the limits with these aren't usually that complex. Usually just kind of sub it in and see what we get back. And I've got x plus 1 for my left-hand side limit. And left-hand side means I put that little tiny negative right there. And then I got x squared minus x minus 2. So I'll just sub 1 into this and see what happens. 1 plus 1 all over 1 squared minus 1 minus 2. So on top I get 2. And on the bottom I got 1 minus 1, which is nothing. And then divide it by negative 2, which is negative 1. So the left-hand limit exists. Somebody might be thinking, like, what happened to my little tiny minus sign here? That doesn't really matter when I'm subbing it into a limit. There are situations where it might matter, but this is not one of them. So I just made a video about absolute value, and if you're interested in finding more about that little left-hand and right-hand side, you can probably check that out. And here I go plugging my own videos again. What a selfish guy I am. All right, so next one, we chose the right-hand side. So the right-hand side is represented with a little plus. And all we do is we sub that 1 in there. So we got 3 minus 1 squared. And you always want to put that in brackets to make sure we know what we're doing. And we do the math on that. And we get 2. All right, so obviously we got something going on here. There's some type of discontinuity happening because we violated the second rule of the definition of continuity, where the limit must exist. We know that if the one-sided limits are not equal, then the limit does not exist. And the best analogy I can give it to you is this is a broken bridge. So if you have, and maybe I'll get the screen up again now. I don't know if I can get that fancy, but you have one bridge coming this way and one bridge coming this way, and they don't meet in the middle. There's a jump that you would have to happen. So literally, if you're walking across the bridge, there'd be a gap or a little step that you'd have to make in order to jump. So that's a discontinuity. So if we were drawing the graph, we'd have to lift our pencil to actually make that happen. So we have to explain this. So if you're in a calculus assessment and you get this happen, you have to explain what's happening here. So first thing we would explain is, let's explain the limits before we talk about the discontinuity. So we would say, therefore, since, maybe that's kind of English is not my real forte. Although I'm a pretty good writer, but not the most grammaristic person, if that's a word. See, I don't even know how to talk. All right, so we said, therefore, the one-sided limits are not equal. So that's huge. That's probably one of the first things you learned in your calculus course when you're talking about limits. In order for a limit to exist, the one-sided limits need to be equal. So therefore, the one-sided limits are not equal, and we can say the limit as x goes to 1 of f of x does not exist. All right? So that's the first thing that I try to train. I don't like that word. The first thing I try to get my calculus students to understand is that you have to explain the step. Why is the step broken? So the step of the definition of continuity is, does the limit exist? And we prove that it does not exist. So once we have that done, and we've proven that step 2 is violated, then we can make a comment on the discontinuity. So we come over here now, and I'll say thus, and our point that we're checking is x equals 1. X equals 1 is a, and we know that I mentioned it's the bridge. So it's the bridge discontinuity. A lot of times that's what my students will call it. Well, the fancy name for a bridge discontinuity is a jump discontinuity. So x equals 1 is a jump discontinuity. And is non-removable. So a jump discontinuity, you cannot remove it from a function. It is there. There's nothing we can really do about it, and that's why it's non-removable. And so there's our first example of using the definition of continuity to prove that something has a discontinuity. So let's try part B of this question, which is, are there any other discontinuities? So let's go ahead. I'm going to take a snapshot of this because I don't want to have to turn back and forth. Whoa. See if I can paste this down. Whoa. I'm gonna have to get the cursor out now.
2,000 years later.
All right, so it says classify any other possible discontinuities. So we've already explored x equals 1. That's the obvious one. So where we want to check now is we want to see denominators equal to 0. So you want to see if there's any VAs, vertical asymptotes, or points of discontinuity or anything like that that might exist within the individual pieces. So in this piece, we only actually have one denominator. So obviously I need to factor that first. So I'll take x squared, and some people might tell you to do that first. I say leave that till the end and see what happens. So let's factor it. So it's what adds to give you -1, multiplies to give you -2. So it's x minus 2, x plus 1. And let's go ahead now and actually rewrite that top piece. So we can say x plus 1 all divided by x minus 2 and x plus 1. So we got a couple points that we would want to check. This point is going to give us, and again, where this comes from is just taking this little guy and solving it. So there's a point here, x equals 2, that we may or may not need to check. And here's another point here, x equals, well, x plus 1. Let me scratch that out instead of getting the eraser. X plus 1 equals 0, and then x equals -1. So some people might be looking and saying, why aren't you canceling this? It's debatable whether or not you would want to do that. When I'm thinking of this and the way I do things is, I think the way I teach things is not about what would I do, because obviously I have a math degree, I have a somewhat deep understanding of all this stuff. I'm teaching the student who's trying to get through calculus. This might not be this might not be their future, math, science. This might be just required for the program, or just want to challenge themselves. I teach it the way that I think most students will get it right. The students who are naturally gifted, or are going to go on and do engineering or calculus or whatever, or science, or even you can be naturally gifted and do nursing or plumbing or whatever. But the students who are naturally gifted at math will figure out the best way to do it without me. I try to figure out the best way to do it for the students who are maybe struggle or need to work out a little bit harder, or just not that interested in it and just want to get through the course. So in my opinion, it's best not to cancel, and you'll see why that is. So now that we've found these points, I'm going to start with x equals 2. And the first thing I do is I check the interval. So if I look at the interval, I ask myself, is 2 in this interval? Because this interval that it comes from, 2, has x less than 1. So obviously x equals 2 does not fit in that interval. So it does not need to be checked. So if I put 2 into this, it will show a discontinuity, but this guy will actually never be 2 because it's always for just x is less than 1. So it's kind of like a trick. They try to get you to check it and try to get you to fail, but you always got to think back to that interval. Is it actually there? So for example, x equals -1. That is in this interval. X is less than 1. So we need to check it. So we're going to check x equals -1. And we'll go ahead and do the first step, f of -1. And I'll show you why I love to do it this way. So the next thing I do is I'm going to sub this x equals -1 into either of these. So either this one here or this one. Personally, I prefer this guy. The reason being is because I haven't altered that guy in any way. So I know it should be a discontinuity if I did it correctly. So let's see what happens. So I sub -1 into where x is. So -1 plus 1, all divided by -1 squared minus -1 minus 2. And I end up with 0 on the top. And on the bottom, I got 1 plus 1 minus 2 is 0. So I get 0 over 0. So I've almost used it again. My students have figured out that when you get 0 over 0, because you've done those limits before, that is a removable discontinuity. You can literally remove it from the function and then continue on to find the limit. So the removing part comes from, and that's why I don't like them to do it in the moment, but certainly they could actually demonstrate that you're removing the discontinuity by canceling it. You see that I just did it in red. So we can write, therefore, since x equals -1 gives us 0 over 0, this is almost got it. Let's erase that. This is a removable discontinuity. And where it gets its name from is the fact that it can be removed. And the only way it gets removed is because of this cancellation. So guys, this video is running a bit long. It's already at like 16 minutes. So I just want to thank you guys for sticking around. If you did, I'm going to bring you another example. I don't know if it will be tonight, but we'll see. All right. Thank you guys for watching, and I will see you guys in class. Peace.
It's over. Go home. Go.